confusing. Too slow for that. All right, thanks. I was going to say it's great to be back, and then I saw the first two talks. They were amazing. I don't like that because I like to be the star of the show, and I tend to bring down the average now. So I will try to keep things interesting, and I'll talk about dark matter. So how can we actually try to understand this stuff that we can't see, we can't touch, and doesn't actually make very pretty pictures, unfortunately. Okay, so how am I going to start here? Well, all the way back in January of 2016, I decided the easiest way to find dark matter was to do it on Google, since they know everything. And so I looked it up. And does anybody know what the search result came out with here? Anyone want to guess? A TV show. Good idea, but wrong. Anything else? Star Trek, movie. Well, it would take a while to figure out that it came up with Toronto. I don't know if this was an anti-Canada bias, what it was. Literally, this was the first thing that came up on Google. So many things are different in 2018. So I guess the first thing you can see is there were 70 million results. It took 0.59 seconds. If you look it up now, there's over 1 billion results. So that's either progress or regress, I don't know. It only took a little bit longer, but now we actually find some real science on here. So I think that's something we can take away positively from 2018, and I'm going to take it. Okay, so we heard a little bit about dark matter, but I want to talk first about why we need it. And the obvious answer is we don't. Please get rid of it. Unfortunately, we can't do that. Okay, so why do we need it? We can't get rid of it because we need it everywhere, pretty much. And we heard this from Caitlin's talk about galaxy clusters. Basically, the first thing you can say is that it really explains how the large-scale structures in the universe form. So this is the movie of actual galaxies from the Sloan Digital Sky Survey. So this is real galaxies at their real positions. You're flying through much faster than the speed of light. But this shows you how galaxies are distributed in space around us. Okay, and I hope you saw at the beginning of the movie, and now you'll see in different little parts of this, that galaxies aren't sort of placed on a lattice or anything. They're not distributed equally. They tend to clump up together in certain ways, and there tend to be parts of space that are emptier than others. And so you might ask, why would that be? And the answer that we have, we think, is dark matter. So this is actually a movie of how dark matter helps galaxies form. We have this picture where the universe is initially very smooth and homogeneous. There are only very small variations in density from point to point. But those very small differences in density are amplified by gravity. This is called gravitational instability. And that dark matter basically gives the places in the universe where the galaxies then end up forming. Okay, and so what that dark matter really does, it provides the kind of cosmic scaffolding to tell us where the galaxies should actually form. And so this is a time evolution movie. Now what you see is later in the movie, the emptier parts of space are even emptier. The more dense parts of space are even more dense. And that's really what dark matter does. It gives us where the galaxies can actually form and makes it look like the previous picture. Okay. The other thing that it does is it explains the motions of galaxies on a somewhat smaller scale. So this is by now your favorite galaxy cluster, if you know one galaxy cluster. Caitlin showed this one also, Abell 1689. So this is just the very central region. But even back in the 1930s, people were able to measure velocities of these galaxies inside of this cluster. And what they noticed is if you measured the galaxy and you used Newton's laws or Einstein's laws, you could figure out how fast the galaxies should be moving. So they expected them to be moving exactly like this. Now that is not exact at all, right? But when they observed them, they were moving much faster. And so really, there's a couple of explanations. The observers are wrong. So as a theorist, that's usually my go-to explanation, but I think you couldn't argue this one away. The other option is that basically the velocity squared is proportional to the mass divided by the distance from the center. So if it's the same galaxy, it's the same distance from the center, that means there must be a lot more mass than what you would accounted for by just the mass, even in the gas and the stars in this system. So galaxy clusters tell us there's missing mass, and that's more evidence for dark matter. On even smaller scales now, it also explains the motion of stars and gas within galaxies. So this is one of our nearby neighbors, M33. It's a galaxy that actually orbits around the Andromeda galaxy. And if you really thought of what dark matter might look like, or sorry, what how the galaxy might behave, you might expect that the galaxy would rotate in a certain way. That is, from the center, you'd have sort of not very fast rotation, but where there's a lot of the mass, you should see a lot of the rotation. And then once you get past the edge of the mass, you shouldn't see much rotation anymore at all. So you might expect to see something like this. If you look at the velocities of stars, say, or the velocity of the gas in the galaxy, that is, past the edge of the galaxy, you wouldn't see much velocity because there's not any mass. Instead, what was observed is something very different. The velocity kept basically as flat here. So there was a lot more velocity than expected. Again, that means there was a lot more mass than expected. And this is exactly what we mean by dark matter. So overall, basically dark matter is what's providing the cosmic glue in galaxies and the underlying foundation for all cosmic structures to form. So dark matter is really important on a variety of scales in all of our studies of astrophysics. So what do we know about dark matter? This is going to be fairly short, okay? Yeah. I know a lot more, but I'm not allowed to tell. It's a conspiracy. Okay, so it interacts with gravity. Right, that's what we know about dark matter, really. That's how it's been seen. So that's the one force that we know it interacts with. So that's our entire basis of our ability to study dark matter. We do know some other things. One other thing we know about it is that it probably moved very slowly in the early universe. So you might say, okay, how do we know that? And the idea here is that if dark matter moved faster in the early universe, it would have wiped out those little seeds of the structure that actually turned into galaxies and other structures that we see around us today. So let me show you a couple of movies of the same object, one where dark matter is moving slowly, that's on the left here, and the other is dark matter moving fast, and that's on the right. So we have original names for all these things, so we call this cold dark matter, and we call this hot dark matter or warm dark matter. And what you can see is if dark matter is cold, that is if it's moving slowly, it allows it to clump up on a lot more scales than if dark matter is moving fast here. So you can see the big lumps are the same in these two, but there are just lots more little lumps in the case where dark matter is moving slowly. And this is a much more consistent picture of the universe than a very cold or very hot dark matter universe. What else do we know? Well, we know it has negligible interaction with light. That's why we call it dark matter. No, but also that means basically it can't condense up very well. Okay, so dark matter, even though it's more massive on average in the universe than normal matter, it doesn't collect up as well as normal matter, and that's because it doesn't interact with light. It's also very hard to measure in the lab, so it doesn't interact with light, but it also doesn't seem to interact, at least as far as we can tell, with either atoms or nuclei. So basically, we've learned a lot, and we've learned almost nothing. So we know it interacts with gravity, and we know it doesn't do much else. Okay, so what else would we like to know? Well, the obvious one is how can I make some money off of this? And yeah, so if anybody wants to hear about my multi-level marketing scheme after the show, it's a very low initial investment. No. Well, so one of the things we'd really like to know then is what is this smallest scale at which it collects up? So what's the smallest scale that we see dark matter structure on? Because that really would tell us directly about how fast it was moving in the early universe, and that would tell us a lot about the dark matter. And we also would like to know what kind of particle is it? What's its mass? What's its interactions with other particles? Is it just very weakly interacting with the normal matter in the universe, or is it kind of completely decoupled and only feels gravity? And the other things we'd like to know is what is it telling us about other parts of physics we don't know. So there's dark energy, which is only related through the term dark. But maybe if we actually understood dark matter better, there would be a more fundamental or deeper connection. Okay, so why is it so hard to find dark matter? Well, some of the explanations were there before, but let me just give you a sense of how difficult it would be to actually look for this stuff around us by looking for its mass. So in the entire universe, there's something like 6 times more dark matter than normal matter by mass. Okay. But if you look at our location in the galaxy and you say, well, let's go from the galactic center to us at something like 25,000 light years from the edge of from the center of the galaxy, and you just average all of the normal matter in that sphere, you average all of the dark matter in that sphere, it would be about as much dark matter as normal matter. And incidentally, it would be a very low number. So 1 hydrogen atom per cubic centimeter. Okay, that's tiny, tiny, tiny. If you go to our solar system, there is 10 to the 17, I won't try to read the zeros off here, times more normal matter than dark matter. That is, if you average all of the matter from the sun and the earth, it's basically all the matter that's from the sun, right, and the inner planets, and ask how much is that relative to how much dark matter, it's 10 to the 17, so that's a 1 with 17 0, times larger than the dark matter. So basically, if you were trying to look for the dark matter in that sphere, it'd be like trying to find the 1 grain of sand that was some weird grain of sand out of all of the sand on the entire Earth. I don't even like trying to find that 1 grain of sand that's sort of scratching me after I get to the beach. So this sounds like a terrible problem to me. But it gets even worse. If you just say at the Earth's surface, so if you just look at the volume of the Earth, you take the mass of the Earth, divide by the volume, and what's the density of normal matter, and you ask how much is dark matter relative to that, well, at the Earth's surface is something like 10 to the 24. That's a 1 with 24 zeros. I think I counted it right, but nobody looked too carefully. I'm a theorist, so it's all fine. I can explain why it's wrong. Right, so there's 10 to the 24 times more normal matter than dark matter. And so this is basically like looking for that one weird star out of every star in the entire observable universe, and that's including the ones we can't see because of dust and all that stuff that we heard from Keith's talk. So it's almost impossible to think about looking for dark matter through its gravity very near us. And this is the exact reason why. Normal matter just dominates over dark matter everywhere. And that's because normal matter can cool down and condense into these little objects. So there were trivia questions, right? None of them involved me, so I cried a little bit. It was a lot, actually. And then I decided I was going to take my ball and go home and have my own trivia. Okay, so special edition trivia, prize, the feeling of contentment, knowledge is power, all that stuff. Okay, so how much would you have to stretch the Earth's radius before its density was the same as the average density of normal matter in the entire universe? So what do people think? Who thinks you'd have to stretch it by a factor of 10? No. Oh, rejected. Okay, this is the worst quiz ever. How about a factor of 10,000? Still not getting many takers. How about a factor of 1,000,000? Yeah, that's a big number. All right, we like that. How about a factor of 10 billion? Yes, okay. Well, that is actually exactly correct. So you have to spread the Earth over a factor of 10 billion in radius. So that means the Earth is overdense relative to the universe as a whole by a factor of 10 to the 30. So we really live in a special place. Basically, that means you'd have to spread the Earth's material out past Alpha Centauri if you wanted to ask what the universe as a whole kind of looked like in terms of normal matter. So clearly time to give up, right? Well, not today anyway. So we're still at this. How are people looking for this? The first way is you can try to put a dark matter detector underground on Earth. So what you can do there is you try to shield your detector from all kinds of sources of other stuff, and you just hope that dark matter, which travels through the Earth like it wasn't there, might very once in a while hit something, and you'd see that. Okay, and so you could actually discriminate between normal matter and dark matter, and well, we haven't seen this. So But the way people do this is pretty amazing. They gather up like a ton of xenon. I mean, literally a ton. Those are the actual experiments now. They're 1 ton of purified xenon underground. You want something very inert, okay? And so people are still very hopeful that they can actually detect dark matter directly. This is a dark matter lab. The other option might be a production machine. This is the Large Hadron Collider. It's a particle collider outside of Geneva, okay? And so what it does is it accelerates protons really fast, technically. And you can actually see this is a person down here. This is the accelerator tube here itself. So person down at this bottom here. Okay, it's an enormous machine. And you might hope that if you smash protons together enough, maybe some dark matter will come out. Hasn't happened yet. So fortunately for me, that means the best option is to go back into the universe, okay? And you could go anywhere you want into the universe to look for dark matter. Again, dark matter dominates on these large scales because gravity is what the force that dominates there. But the best place might be our own Milky Way. So we heard talk about galactic archaeology and what the Milky Way looks like to an observer. This is what the Milky Way looks like to me as a theorist. Okay, so if you had dark matter eyes, this is what we think the Milky Way would look like. The Milky Way disk would sit at the very, very center here. It would barely even be noticeable, right? Who cares really, us in this middle of this thing? What we really care about is that dark matter stuff, yes. And again, there's millions and millions and millions of lumps of dark matter. This whole range here, this would be something like 2.5 million light years now. So it's an enormous distance. And so I've kind of highlighted one of these lumps, and the reason for that is that we think that these lumps host galaxies. So this is the Fornax dwarf spheroidal galaxy. It's just kind of a ball of stars. It's 1,000 times fainter than the Milky Way, but I think you can kind of see it there pretty easily. And just like those galaxies moving around in clusters, you can measure the velocities of the stars in these galaxies and see that they're moving a lot faster than they should be. That's why we think there should be dark matter in there. But this isn't the faintest galaxy we know of. This is the Draco dwarf spheroidal galaxy. It's 100,000 times fainter than the Milky Way. So this was actually discovered by people staring at photographs of the sky, photographic plates, and what they'd do is they'd say, if I look at the left side of this image, it seems like there might be a bit fewer stars than the right side of the image, maybe the galaxy's there. And it turns out that's actually confirmed by me drawing a circle and telling you there's a galaxy there. Trust me, I'm a doctor or something. No, but so again, you can see that all those stars, they are moving with the same velocity, okay? The Milky Way stars are typically moving at 200 kilometers per second, and they have differences of 200 kilometers per second. They're all moving the same to within around 10 kilometers per second. But even that 10 kilometers per second still tells you there's a lot of missing mass here. And the really cool thing is the fainter you go here, the more dark matter you end up with. So if we look at the total mass that you can measure in these galaxies compared to the observable mass, you get the Milky Way here at around 10 to the 11 solar masses in stars, and you don't really need much dark matter in the center of the Milky Way. If you take that Fornax galaxy, you get here, so maybe 10 times as much dark matter as normal matter. That Draco galaxy is here, okay? We can do simulations too, Caitlin, and it doesn't even have to be, no. And the winner, yes, this is the faintest galaxy we know of. It's the Segway 1 dwarf galaxy. It's only 100 times the luminosity of the sun, but it has dark matter content that's 2,000 times the content of the stars there, okay? So what we'd really like to do, though, is understand where that stops. So not all of these lumps will host a galaxy. And what's a really fundamental question is, how can we look for these lumps that don't have a galaxy in them? Remember, the only way we've seen things is by looking at light. And so we know that these massive lumps, they have most of the mass in the Milky Way, but there are relatively few of them. These tiny ones don't have most of the mass, but they're an enormous number. In fact, the smallest of them is predicted to be about an Earth mass, and we think there might be 1,000 trillion of those inside of the Milky Way floating around. So how could we see that? Well, gravity to the rescue again. This is an image of galactic cannibalism that we heard about from Keith's talk. This is a galaxy like the Milky Way. This is an artist's rendition, of course. A galaxy like the Milky Way. And this is a galaxy that's fallen into the Milky Way and is being tidally disrupted. It's being cannibalized by the Milky Way. So I have a second simulation, and the idea would be, what if the Milky Way had a ton of these tiny lumps floating around? So it has these ghostly lumps down here, okay? And if it happens to fly through the stream, yes, simulation, very accurate, what might you see? Well, what you might see is, if nothing had hit it, you'd see this. That's what they call a regular stream here. But what you see in some of these observed streams are these gaps. So you don't see the same brightness in stars everywhere. You see the same brightness here, and then you see a dimming in this part, and you start to see the stars again over here. Okay? And what that means is maybe that this gap came from one of these dark lumps flying through that stream. So maybe these streams can actually act as dark matter detectors. And the other option we heard about from Caitlin as well is gravitational lensing. So again, gravitational lensing, what it does at heart is it takes a light ray and it actually bends that light ray. So it would have, if it had not passed this massive object, it would have gone straight and gone somewhere else, but instead it got bent and came to us here. Okay, and so this angle between the real position and the observed position is kind of a deflection. And gravity can help us there too, because these clusters or even individual galaxies can maybe tell us something. So what you're seeing here is, hopefully we can detect a tiny dark matter lump just by how it's perturbing this gravitationally lensed arc. And the hope is that in future surveys we'll have thousands, or well, at least hundreds of gravitational lenses, and that may provide us this dark matter detector to look for mass where we don't see any light whatsoever. And that would really tell us a lot about this dark matter. And, of course, here in the University of Texas, we're involved in the Giant Magellan Telescope. And this is going to be essential for this in a couple of ways. As an enormous collecting area. So again, they always put people for scale. The people are down here, right? So this really is a giant telescope. It's not a misnomer. Has an enormous collecting area, which means we can see fainter galaxies. And it's also sensitive then to smaller angular deflections, so we can hopefully see smaller lumps of dark matter. And for me, Texas is also a great place to be because we have the biggest supercomputers in the US that aren't running things that we're not allowed to talk about. And so they all have cool names like Stampede 2. We've got Frontera coming along. It's a $60 million machine. Should be online next year. And so this really gives us an edge in trying to make the predictions for all of these kind of observations that are coming along. So I'd say there's a tremendous amount of excitement here. There's a lot of mysteries in the universe that we have yet to unravel. But even though we haven't directly measured dark matter's properties, we understand a lot about it, or maybe a lot more than you would have thought. And to me, it's really exciting, this idea that by studying either the tiniest nearby galaxies, or measuring the properties of these shredded star clusters, or looking for the deflections of light in otherwise empty space, we might really learn the secrets of this stuff that forms the glue to the entire cosmos. So I'll end with a movie of how the Milky Way's dark matter halo would have formed, and take any questions you might have. Thank you.
The hat is back.
The hat is back.
All right, let's take a couple questions from our third speaker. We'll start up here on the balcony.
So the question was, in the underground detectors that I was talking about, what kind of interactions are we expecting to see? And the idea here is these are typically just elastic collisions between a dark matter particle and an atomic nucleus. So it's not that dark matter and atomic nuclei never interact. It's just they interact so infrequently that we just wouldn't see it unless we could shield everything else and have a ton of purified liquid xenon 1 mile underground. So if somebody else has done that and already ruled this out, that's great. But that's why it's really hard to see. So it really is just collisions of nuclei with dark matter.
All right, how about right there?
So the question is, how do you think gravitational wave detection can help you study dark matter? And I think that's an excellent question because there was an enormous amount of interest in the possibility that dark matter might actually not be these sort of fundamental particles after the gravitational wave results came out, that it might actually be the black holes that were forming the signal for the gravitational wave detections. And so I think this is a great instance of the scientific communities coming together, because immediately people started writing papers saying, of course, dark matter is black holes, and that's very appealing. But then immediately other people started saying, well, if that was the case, here's a number of things that could go wrong. And so, for example, gravitational lensing by these 30 solar mass black holes would mean we know how much dark matter there is in the Milky Way. We should have seen some gravitational lensing of stars in the Milky Way just from these black holes. And so I think it's actually, it's helped us rule out things. It hasn't helped us rule in things, unfortunately, but maybe that's the future here.
All right, another question. How about you right there?
Trust me, I'm a doc. No, yeah, so it's excellent question again. So basically, gravitationally, it wouldn't be anything, but we know from the basic properties of how it clumps up on larger scales, how smooth it should be nearby. And so we don't know it, I'd say, to a decimal place there, but we definitely know the average density around the sun, and that should pretty much be the same in the solar system and everywhere throughout the solar system. The one exception might be there's some theories where you could actually collect up dark matter at the center of the sun, and then actually if that dark matter starts interacting with itself, you could do some crazy cool things and maybe change nuclear reaction rates in the sun, do all kinds of stuff. So yeah, there's all kinds of things you can figure out. Since we don't have any actual observational evidence for this, it really makes particle theorists really happy, and there's a ton of crazy or exciting models depending on your perspective about this.
All right. Yes, up here in front.
How confident are we that what we're interpreting as dark matter isn't some large-scale phenomenon with gravity that we don't understand?
Right. So the question is, how confident are we that what we're interpreting as dark matter is actually dark matter and not some modification of gravity on larger scales? And I think that's an excellent point. It is a big leap to say that there's this substance that we haven't ever really detected other than through its gravity. Maybe couldn't gravity be different than what we think? The problem is that it's really hard to mess a little bit with Newton's laws or Einstein's laws and not mess up a lot of things. And so there's no theory that really explains the scales of galaxies, the scales of galaxy clusters, the scales of superclusters, the scale of the universe, and still actually reproduces a solar system that is a modified theory of gravity. And that doesn't mean it's not possible to do, but it's really, really hard to do that without really messing up a lot of things. And so the dark matter here, just this one kind of extra dark matter, so this missing mass that just interacts gravitationally, really explains all of these observations over a wide variety of scales. And I think that's why people feel fairly confident in it. But you're absolutely right. We should be considering these as alternatives as well.
So I think a question a lot of people have, and you kind of alluded to this in your talk, is that they might have heard of this thing called dark matter. They might have heard of this thing called dark energy. And if I know one formula, it's equals mc squared. So matter is energy. So are they the same? Are they not the same?
Excellent question. They are not the same, and anybody who does that, the elf on the shelf will come and arrest you. No, okay. So dark matter and dark energy are very, very different. So dark energy is something It seems to be a property of empty space. So dark matter is matter like any other kind of normal matter. If you stretch out a box of dark matter, its density goes down. If you stretch out a box of dark energy, its density stays the same. Okay, so somehow this is a property of empty space that doesn't change as the universe expands. So everything else dilutes as the universe expands. If you have 3 atomic nuclei in some region of space and you stretch that space by a factor of 2 in each dimension, then you have 8 times larger volume, and so you have 8 times smaller density. That's the same for dark matter. So dark matter really is matter like normal matter that we think of, atoms, particles. Dark energy is something very, very different. It seems to be just related to the property of empty space. It doesn't clump up in any way that we know of, and it has this weird property that it seems to start pushing the universe to accelerate its expansion on large scales. So I think it is a good question. It was very confusing nomenclature, but they are very different.
I always like to think of it as dark matter. It's dark because, like you said, it doesn't interact with light. Dark energy we call dark because we have no idea what the hell it is. Another round of applause for Director of Dark Matters.